Howdy, this is Yu-Sheng. Today I'm going to present you a paper, End-to-End Differentiable Learning of Protein Structure. This paper is from Cell System 2019. The main topic of this paper is to propose a modern method for predicting protein folding. This task is to predict the protein sequence to 3D structure. And more specifically, this is to determine the spatial arrangement of atoms within a protein molecule. The significance of this task is that it is important for understanding protein function and thus can help drug discovery and design. However, there are some gaps for existing methods. For example, they are human engineered, so that might not be suitable for large-scale prediction problems. And this paper introduces an end-to-end differentiable, basically deep learning model for predicting protein structure from sequence. And they claim that they optimize global geometry without violating the local covalent chemistry. What is thrilling is that the model achieves state-of-the-art accuracy in predicting normal folds and pretty close to the state-of-the-art for known folds. So before this method is proposed, let's look at the previous computational methods for protein structure prediction. Basically falls into two main categories. One is explicit sequence to structure mapping. So this basically involves physics-based simulation and fragment assembly methods. And as we can see, since it's basically physics-based, it would use lots of computational cost to simulate. So the downside of this kind of methods is that they are restricted by computational cost to small proteins. Another category is coevolutionary methods. They identify co-evolving residuals within protein families to derive contact maps, aiding in structure prediction. However, these kind of methods are unable to predict structures for which no sequence homologs exist. In other words, the novel protein design may not be feasible for these kind of methods. So that's why they proposed the recurrent geometric networks, aka RGNs. So these two issues are what they wanted to solve. So what exactly is the approach? This is the overview of the model. As we can see, the input is a protein sequence, and the output is a predicted structure, is a predicted 3D structures, giving coordinates of each amino acid, basically, of course, atoms. This is the main model of the RGNs. You can see that it is consisting of two kind of units. One is computational unit, one is geometry units. So what exactly is computational unit? It's a bidirectional LSTM. So it can help to integrate some additional information on a single amino acid. Integrate what? Integrate the global, let's say the whole sequence, the information of whole other amino acids to this specific amino acid to get the neighboring information. And this computational unit will output some predicted angles for geometry units for further computation. So what geometry units are doing is that it takes one amino acid, and we have some predicted angles, and we'll learn how to put those atoms. These are predicted angles for atoms, right? So this geometry unit is trying to put these angles and atoms into some kind of angles. And as we can see, this is a sequence here. So first we have one amino acid and we add one, so it will be two amino acids, or say residuals. It will be keep adding and adding, and the end output will be the predicted structure. And what the geometry unit is doing is that we can see that here, existing atoms, we have the input, and we do some rotation, some extension, some torsional rotation. This is basically the geometry unit is doing. Here, we can see the overall output of the model is a predicted structure, and we want to check if this is good. So this is basically describing the loss. How do we calculate loss? So it's from you compare the predicted structure with the experimental structure, which is basically the ground truth, using DRMSD. I will describe this in detail later. So this is basically the loss calculating, and will back propagate into the model, so to update the model weights. Here, let's look into the computational unit. The computational unit is basically a many-to-many bidirectional LSTM with 3 output angles, as I just described earlier. Here, I want to focus on this output. This output is using a torsional alphabet. Don't forget, this output is to output 3 torsional angles. And how do we choose these torsional angles? We're using some torsional alphabet. This is predetermined. Let's say you can think of it as a dictionary of predetermined angles, and we mix these angles using circular projection, and we mix these angles using weighted average. How is this weighted average decided? It's from this. It's from the model itself. The LSTM will decide what will be the weight. Yes, as I just mentioned earlier, the geometry units basically do these 4 things: adding, rotating, extending. Basically, is trying to modify the coordinates of the atoms. So let's talk about DRMSD. So this is a loss function. It will also be using as a metric. On a higher level view, you can think of it as the distance, as the average distance of predicted structure and experimental structure. How is exactly it is calculated? You can see like CJ and CK. CJ and CK, it is the L2 distance, pairwise L2 distance within a given protein structure. So this is the pairwise L2 distance. So we get let's say this is the predicted protein structure, and this is the pairwise distance between the components here. And then for this predicted protein structure, we calculate this pairwise distance, and the experimental structure, which is the ground truth, we also calculate the pairwise distance, and then we subtract we subtract each other, and we get a matrix, which is matrix D. That is the distance that is telling you the distance, the distance between a predicted structure and experimental structure for each atom or each component. So we have this one, and we want to use this distance with we want to represent the distance of this predicted structure and experimental structure with one value. So we take the L2 norm of this matrix, and L times L minus 1 is just a normalized term. Let's talk about experiments. So the model assessment, they follow the critical assessment of protein structure prediction, shorthand CASP or CASP. So this is a procedure that that assess methods, prediction methods in a blinded fashion by testing predictors using sequences of solved structure that have not been publicly released. So let's talk about the evaluation metrics. There are two metrics here. One is DRMSD, which I just mentioned before. Another one is TM score. Why? Because DRMSD assesses prediction at all length scales, and it penalizes large global deviation in proportion to their distance, resulting in very high errors for far apart regions. And also, it is invariant reflections. So you will have to do some correction for the model if you train based on DRMSD. So due to some shorthands of this metric, the paper authors they also use TM score. So this is the equation of TM score. I'm not going to the details, but what we have to know is that TM scores range from 0 to 1, and more is the more the better. And here we have a basic standard criterion to evaluate how good or how match two protein sequences are, how similar two protein sequences are. So here, if the TM score is less than 0.17, it corresponds to random or unrelated protein. And if TM score is greater than 0.5, it generally corresponds to the same protein fold. Also, it's not invariant to reflections. The dataset is recreated by past CASP conditions. Note that I mentioned that CASP is method. You have to assess methods in a blinded fashion. So basically some of the data, so they take protein net data set and they made some of them blinded. So it's like blind phone. It's like a testing data set here. But they follow the CASP style procedure. So they created corresponding protein net test sets for CASP through 12, including CASP structures. So they made them CASP-like. Yeah, and also they utilize multiple CASP dataset for comprehensive assessment, spanning various dataset size. We will see that later. So to test this proposed method, they use two kinds. One is free modeling FM. One is template-based TBM and TBM hard targets. So one of them is about predicting novel folds. Another one is predicting folds that are known already in protein data bank. So I would say that the experiment utilizes two kinds of data sets, protein nets dataset and protein data bank dataset in CASP dataset style. Okay, these are the experiment results. So this table is about DRMSD. So we can see that, as I mentioned, DRMSD lower is better. So it's basically the distance between the predicted protein fold and the round truth protein fold, and the average distance will be measured in all. So here we have RGN, which is the proposed method, and these the first server to the fifth server, they are using co-evolution methods, and they are basically the winner for CSP 7 to 12. So, for example, this is the CSP 7, the best result for CSP 7. The server does a really good on CSP 7. So we can see that RG and this table is for novel faults. The table on the right hand side is about known faults. So we can see that RGN outperforms every server, every co-evolution method from CSP 7 to CSP 12. But for known faults, it is having a inferior result to the best of the CSP co-evolution server. But however, we have to note that they have only like 1 to 2 or distance from the best server. So that's the conclusion of this experiment on DRMSD. Novel faults, they achieve the state-of-the-art accuracy. The known faults comes within 1 to 2 or versus the best co-evolution server. Also, they made experiments using TM score. The experience set is the same, but we can see that for TM score, they are having the position, the rank between the fourth server and third server for the normal faults. However, we have to know that, and then for known faults, they are also having relatively inferior results. However, we have to note that, see here, the TM score of RGN on known faults are very close to 0.5, which means that it generally corresponds to the same protein fault. So it still perform not very bad. So to conclude this paper, so RGN showcases promising advances in protein structure prediction, and it outperformed existing methods in predicting novel faults, and are very close to the state-of-the-art, which is co-evolutionary servers in known faults. The most important is that they are not relying on co-evolutionary data or structural templates. So it is, in some sense, more robust, and it has some potential. Future directions may involve incorporating additional information such as structural templates or co-evolutionary data. Also, for my personal critique, I would say that they could integrate some physics-informed mechanism in the LSTM-like model, which may help further restricting the output result and make them more realistic. So even though they claim to avoid violating local covalent chemistry, they use the torsional alphabet, I'm personally not very convinced, since this is just choosing from correct states, but this does not ensure that the physics rules are followed in general. Thank you, and this is the end of my presentation.